Hi everyone, welcome back. In this video, we will discuss top Apache Kafka interview questions and answers. Let's begin. What is Apache Kafka and why is it used? Apache Kafka is a distributed high-throughput event streaming platform used for building real-time data pipelines and streaming applications. It allows applications to publish and subscribe to streams of records in a highly scalable, fault-tolerant and durable way. Kafka is used because it handles extremely large volumes of data with very low latency, making it ideal for modern systems that continuously generate events such as logs, user activity, transactions, sensor data, and microservice events. A major reason companies adopt Kafka is its ability to decouple producers and consumers. Producers write data to Kafka without caring who reads it, and consumers read the data at their own pace. Kafka stores all data for a configured retention period, allowing reprocessing and replaying whenever needed. Kafka's distributed design enables horizontal scaling simply by adding more brokers. Its durability is ensured through replication across brokers. These features make Kafka the backbone of streaming analytics, event-driven architecture, fraud detection, logging pipelines, and microservice communication in large-scale enterprises. Next, what is a Kafka topic? A Kafka topic is a logical channel or category where messages are published by producers and consumed by consumer applications. Topics act as containers that store records in append-only logs, allowing Kafka to organize data streams efficiently. Each topic is divided into partitions, which makes Kafka horizontally scalable. Because partitions allow parallel reads and writes, topics can handle huge data volumes without performance bottlenecks. A key advantage of Kafka topics is that data is retained for a configurable period, regardless of whether consumers have processed it. This means multiple applications can consume the same stream independently at different speeds without interfering with each other. Kafka also allows consumers to rewind and read old data again because topics do not delete messages immediately after consumption. Topics are central to Kafka's architecture because they provide fault tolerance, durability, and scalability while enabling flexible event distribution across systems. Next, what is a Kafka partition and why is it important? A Kafka partition is a segment of a topic that allows Kafka to distribute and scale data across multiple brokers. Each partition is an ordered, immutable sequence of messages where each record has a unique offset. Partitions allow Kafka to achieve massive throughput because producers and consumers can work in parallel across different partitions. When a topic has multiple partitions, Kafka can spread these partitions across brokers so the load is balanced. This ensures high performance even during large workloads. Partitioning also preserves order within a single partition, which is important for event-driven processing where sequence matters. Consumer groups rely on partitions for parallelism because each partition is read by only one consumer in the group. Partitions also support replication, meaning data is copied across brokers for fault tolerance. If one broker fails, another broker containing the replica takes over immediately. Overall, partitions make Kafka scalable, resilient, and fast. Next, what is a Kafka broker? A Kafka broker is a server responsible for storing data and handling read and write requests from producers and consumers. A Kafka cluster consists of multiple brokers, each managing partitions of various topics. When a producer sends data, the broker responsible for that partition stores it on disk and replicates it to follower brokers for reliability. Brokers are designed to be stateless in terms of client identity. They store only the topic partition data and metadata required for leadership. If one broker fails, Kafka automatically shifts leadership of affected partitions to follower replicas, ensuring continued availability. Producers and consumers automatically discover new leaders through cluster metadata, allowing seamless failover. Kafka brokers handle very high volumes of reads and writes due to optimizations like sequential disk I/O, zero copy mechanisms, and batching. They scale horizontally by simply adding more brokers to the cluster. This architecture makes Kafka suitable for enterprise-grade streaming workloads. Next, what is Zookeeper's role in Kafka? In traditional Kafka deployments, Zookeeper is used to store and manage cluster metadata such as broker information, topic configuration, partition assignments, and leadership roles. Zookeeper ensures coordination within the cluster by tracking which brokers are alive and managing partition leader elections. When a broker goes down, Zookeeper identifies the failure and triggers a leader election among followers. It also maintains access control lists and configuration settings for the cluster. Without Zookeeper, older Kafka versions cannot operate because brokers rely on it for distributed coordination. However, Kafka is gradually replacing Zookeeper with its own internal consensus mechanism called KRAFT, Kafka Raft. KRAFT removes the need for external coordination, simplifies deployment, and improves scalability. Despite this transition, understanding Zookeeper is still important because many existing clusters continue to use it. Next question: what is a Kafka producer? A Kafka producer is a client application that sends or publishes messages to Kafka topics. Producers decide which topic and which partition to write to, either automatically or based on a custom key. Kafka producers are optimized for high throughput using batching, compression, and asynchronous sending. Producers also support different acknowledgement modes to control durability. They can wait for acknowledgement from no brokers, only the leader, or all replicas. They also support retrieve and idempotent mode to guarantee no duplicate messages. Producers can evenly distribute data using a round-robin strategy or maintain ordering by sending all related events to the same partition using keys. Kafka producers form the entry point for data ingestion from microservices, applications, sensors, and logs. Their reliability and speed make Kafka suitable for large real-time pipelines. Next, what is a Kafka consumer? A Kafka consumer is an application that reads messages from Kafka topics. Consumers belong to consumer groups, and Kafka ensures each partition is consumed by only one consumer within the group. This makes consumer groups powerful for parallel processing. Consumers track their progress using offsets, which represent the position of messages they have processed. Consumers can automatically commit offsets or manually control them for precise processing. Kafka does not delete messages after consumption, allowing consumers to rewind and reprocess data. This flexibility makes Kafka ideal for analytics, log processing, ETL pipelines, and event-driven microservices. Kafka consumers handle large message volumes efficiently and can scale simply by adding more consumers to the group. Next, what is a consumer group in Kafka? A consumer group in Kafka is a collection of consumers that work together to read messages from a topic. When consumers join the same group, Kafka divides the partitions of the topic among them. This ensures that each partition is consumed by only one consumer within that group, allowing messages to be processed in parallel without duplication. Consumer groups make Kafka highly scalable. When more consumers are added, Kafka automatically redistributes partitions, increasing throughput. If a consumer fails, Kafka reassigns that consumer's partitions to the remaining members, ensuring fault tolerance. This mechanism also allows multiple independent applications to read the same topic data simply by using different group IDs. One group may process analytics, another may update dashboards, and a third may trigger microservices. Each group reads the topic independently. Overall, consumer groups provide scalability, fault tolerance, and flexible consumption patterns, making Kafka ideal for distributed systems. Next question: what is a Kafka offset and why is it important? A Kafka offset is a unique sequential number stored with each message within a partition. It represents the exact position of a consumer in the message log. Offsets allow consumers to track where they left off so they can continue reading from the correct point during the next pull. Offsets are extremely important because Kafka does not automatically remove messages after consumption. Instead, it keeps them for the configured retention period. This allows consumers to rewind, replay, or reprocess messages whenever necessary. Offsets enable reprocessing in case of system failures, bugs, or updated business logic. Offset management can be automatic or manual. Automatic commits simplify processing but may cause data loss if messages are not fully handled. Manual commits give developers full control and ensure exactly once or at least once processing. Offsets provide reliability, flexibility, and recovery support in distributed consumer systems. Next, how does Kafka ensure fault tolerance? Kafka ensures fault tolerance through its replication mechanism, where each partition has multiple copies stored across different brokers. One replica is elected as the leader and handles all reads and writes, while the others act as followers and sync data from the leader. If the leader fails, Kafka automatically elects a follower as the new leader, ensuring the system keeps functioning. Kafka also uses durable storage by writing messages to disk before acknowledging producers. This guarantees messages are not lost even if a broker shuts down unexpectedly. Replication combined with durable writes allows Kafka to recover from machine failures, network issues, or hardware crashes. Producers can configure acknowledgement levels to increase reliability. Consumers can replay data because Kafka retains messages for a specified time, enabling recovery from consumer failures. These features together make Kafka a resilient, high-availability data streaming platform for large-scale distributed systems. Next, what is Kafka replication factor and how does it work? The replication factor in Kafka specifies how many copies of each partition Kafka should maintain across the cluster. A replication factor of 3 means every partition is stored on 3 different brokers. One of these replicas becomes the leader, while the remaining 2 act as followers. The replication factor directly influences durability and reliability. If the leader broker goes down, Kafka automatically promotes one of the follower replicas as the new leader. This ensures the partition remains available without data loss. Higher replication factors increase fault tolerance but also require more storage, more network bandwidth, and more synchronization overhead. Most production clusters use a replication factor of 3, which offers a good balance between reliability and resource usage. Overall, replication factor is a key part of Kafka's fault tolerance model, ensuring that message data remains safe even when brokers fail. Next, what is the role of partition leader and followers in Kafka? Every Kafka partition has a one leader replica and one or more follower replicas. The leader handles all reads and writes from producers and consumers. Followers do not accept requests directly. Instead, they continuously replicate data from the leader to stay synchronized. This leader-follower model ensures strong consistency. If the leader fails, Kafka elects one of the in-sync followers as the new leader. This ensures the partition remains available without losing data or interrupting client operations. Producers always write to the leader and consumers typically read from it as well. Kafka ensures that only followers that are fully synchronized are eligible to become leaders. This prevents data loss in failover situations. The leader-follower architecture is central to Kafka's scalability and fault tolerance, helping it handle large workloads reliably. Next, what is Kafka retention policy? Kafka retention policy determines how long messages remain stored in a topic, regardless of consumer activity. Kafka does not delete messages after consumption. Instead, it keeps them for a configured duration or until the log reaches a configured size. Retention policies allow consumers to reread data for debugging, analytics, machine learning training, or error recovery. Time-based retention keeps messages for a defined number of hours or days, while size-based retention deletes older data when the log exceeds a certain size. Kafka also supports log compaction for topics where only the latest value per key is needed. This is useful for maintaining changelog data and state stores. Retention policies give Kafka enormous flexibility compared to the traditional message queues, making it ideal for long-term event storage and replay. Next, what is Kafka's exactly once semantics EOS? Exactly once semantics in Kafka ensure that messages are neither lost nor processed more than once, even in failure scenarios. Kafka traditionally offered at least once and at most once delivery, but modern Kafka supports exactly once through idempotent producers and transactional writes. With idempotent producers enabled, Kafka ensures that duplicate messages are not written when retries happen. Transactions go a step further by grouping multiple writes across topics and partitions into an atomic unit. Either all writes succeed or none do. Exactly once semantics are crucial in financial transactions, billing systems, payments, and critical event processing pipelines. Without EOS, systems risk double charging, inconsistent states, or inaccurate analytics. Kafka's EOS is one of the strongest reliability guarantees in modern distributed systems, making Kafka suitable for mission-critical event processing. 15. What are Kafka transactions and why are they important? Kafka transactions allow producers to send multiple writes across different partitions and topics as one atomic operation. This means all messages in the transaction are either fully committed or fully rolled back. Transactions are critical for applications requiring high reliability such as financial systems, banking workflows, inventory updates, payment pipelines, and multi-step state changes. Without transactions, a failure during message publishing might lead to partial writes, causing inconsistent or corrupted data across systems. Kafka transactions prevent such problems by ensuring that consumers see only successfully committed messages. They work together with idempotent producers, guaranteeing that even when retries happen, duplicate writes never occur. Kafka also provides read process write guarantees through transactional consumer-producer flows, where consuming input and producing output can be treated as one atomic unit. This allows real-time pipelines and stream processors to maintain correctness even in failure situations. Overall, transactions help Kafka support exactly once processing across distributed systems, making event workflows safe, reliable, and consistent. Next, what is Kafka Streams API and how does it work? Kafka Streams is a lightweight Java library that allows developers to build real-time processing and analytics applications directly on top of Kafka topics. Unlike external processing frameworks such as Spark or Flink, Kafka Streams does not require dedicated servers or clusters. It runs inside your application, scaling automatically as more instances are launched. Kafka Streams supports transformations such as filtering, mapping, grouping, joining, windowing, and aggregations. It also maintains local state through embedded state stores, which enable advanced features like session windows and incremental aggregations. These state stores are backed by Kafka topics, ensuring resilience and fault tolerance. Kafka Streams guarantees exactly once processing when combined with Kafka's transactional features. It is ideal for applications that continuously react to new events, such as fraud detection, monitoring dashboards, payment workflows, and IoT stream analysis. Its biggest advantages are simplicity, built-in scalability, fault tolerance, and deep integration with Kafka's underlying log-based design. Next, what is log compaction in Kafka and when should it be used? Log compaction is a Kafka feature that ensures A topic retains only the latest value for each unique key, rather than keeping the entire message history. It is ideal for use cases where the latest state matters more than historical data. Examples include maintaining user profiles, product inventory levels, configuration data, and state stores for stream processing. Compaction runs continuously in the background. If a key appears multiple times in the log, Kafka removes older versions and keeps only the most recent entry. This significantly reduces storage usage while preserving essential state. Kafka never removes messages with null values immediately because null acts as a tombstone marker for deletions. Log compaction is critical in stateful architectures where applications rely on changelog streams to rebuild state after failures. It provides durability, efficient recovery, and predictable storage size while maintaining correctness. Next, how does Kafka achieve high throughput? Kafka achieves high throughput through a combination of architectural optimizations. Messages are written to disk sequentially, which is much faster than random writers. Kafka uses zero-copy technology, allowing data to be transferred directly from disk to the network without passing through the application layer. This reduces CPU usage significantly. Kafka allows batching of messages, compression, and asynchronous writes to improve performance under heavy loads. Partitions enable parallel production and consumption, distributing workload across multiple brokers and CPU cores. Replication is handled efficiently through incremental fetches and leader-follower synchronization. Kafka also minimizes overhead by keeping producers, brokers, and consumers stateless regarding each other's progress. Combined with OS page caching and optimized network protocols, these features allow Kafka to process millions of messages per second with low latency. Next, when should you not use Kafka? Kafka is not suitable for systems requiring immediate synchronous request-response communication because Kafka is built for asynchronous event streaming. It is also not ideal for small-scale applications where maintaining a full Kafka cluster would be unnecessarily complex and expensive. Kafka is not optimal for systems where global ordering across all events is required. Kafka maintains order only within partitions, not across topics or entire clusters. For extremely low latency messaging, microseconds, in-memory brokers may be better choices. Kafka is also not suitable for storing large binary files or long-term archival data because it is optimized for logs, not file storage. Additionally, Kafka is not the right choice if message delivery must happen exactly at the time of request. Consumers control when they read data, not producers. Kafka should be avoided when simpler messaging tools like RabbitMQ or Cloud Queues can meet the requirements more efficiently. That's it. These are the frequently asked Kafka interview questions in the interviews.